Hi, welcome to another video. In this video, we're going to talk about how to create some polynomial functions if we know a couple complex zeros. Now, that sounds really familiar because we've done this before with real zeros. We said, well, wait a minute. If we know that an x-intercept is, say, like x equals 4, then we can say x minus 4 equals 0, and x minus 4 would be this factor of a polynomial that we're creating. And we're going to do something very, very similar, but now with complex zeros. Here's the main thing that you want to learn in this video, is that if you have one complex zero or complex solution, then you automatically have another by this theorem that says that complex solutions always come in conjugate pairs. And so if you have one, you have two. If we have two, what we can do is create two factors, and when we multiply those factors, so distribute, we're going to get what's called an irreducible quadratic factor. And that's part of this function that we're going to build. So we're going to discuss that, we're going to see what it is. One of the main things I want to teach you in this video is how to multiply factors, linear factors that have complex values in them, an easy way, because that's probably one of the main things that students get confused on, is how in the world do you do that. So I'm going to teach you how to do that because we use that in the next few videos. So let's get right into it. Let's talk about what degree means again. Let's talk about if we have one complex, we have another one, create some factors like we did before, and then I'll show you how far I would like you to distribute. And then if you have to distribute all the way, I'll show you how to do that as well. So let's go right into it. If we have a degree 4 polynomial, what that means is that we are going to have 4 linear factors across the complex number system. So polynomials can always be factored into linears and irreducible quadratics across the real number system. But if we go into complex numbers, like we have right there, we are going to have 4 factors. Now, some of those factors might be repeated. So that's like a multiplicity idea. But in general, for every degree, we have that many factors and that many solutions in complex numbers. Not necessarily all real numbers. We have at most 4 real solutions, but we have exactly 4 solutions of a complex. So what we're going to do here is we're going to find 4 factors, and some of that's going to be wrapped up in a multiplicity. The second thing we're going to hopefully understand is that if we have one complex solution, we also have another one that's sort of hidden, but they always come in complex conjugate pairs. So 3 minus 2i, that's great. That's one solution for us. It's giving us that this has zeros of 3 plus 2i and 4 with a multiplicity 2. We can build a couple factors from that. If we have 3 plus 2i, we can get an additional factor by understanding that 3 minus 2i, the complex conjugate, also has to be a solution. That was due to this, the quadratic formula working on an irreducible quadratic. And here's what the whole thing is. If you can factor a polynomial into linears and irreducible quadratics over reals, then that irreducible quadratic is only unfactorable because it has complex numbers in it. And that plus and minus gives us a conjugate pair for complex solutions. That was in the last video that we talked about. So if we have 3 plus 2i, we have 3 minus 2i also, basically by the quadratic formula. And so here's what we're going to do. Number one, we're going to match up and make sure that we have 4 solutions for degree 4. We have 1, we have 2, we have 3, but this says you basically have 4 twice as a solution. That's where the multiplicity comes in. Then what we do is we start building our factors. Please, please don't skip what I'm about to do. It's very common for even teachers to say, hey, just go straight to your factors and do like x minus 4. Easy, just switch the sign. Don't do that. And the only reason why not is because what I want you to do with your complex solutions is very specific. And it will, I promise, help you. And it's much easier to understand if I have you start the way I'm about to show you. So here's what I want you to do. I want you to make each of these solutions an actual solution. For instance, I want us to say, hey, x is going to equal 3 plus 2i. And x is going to equal 3 minus 2i. And x is going to equal 4. Start that way. List out all of your solutions, because by adding or subtracting, respective of what signs we have, we're going to get factors set equal to 0. It's going to make a lot more sense that we can use the zero product property in reverse to create factors of some polynomial. Also, what I'm about to do, especially with our complex solutions here, is to build them in a certain way that makes distribution easier. Otherwise, you have 3 terms and you have to foil it. It's really annoying. So I'm going to do this so that it's structured easier. And if you go straight to your factors, you're going to have a sign error. At least I see that like in 95% of the times I teach this. If I go straight to the factors, students mess up a sign and it does not work out well. So we're going to say, hey, degree 4, we have 4 solutions. Well, one of them's repeated, do that in multiplicity too. So really, we have 3 solutions, one of them just repeated. And we're going to list them out. X equals 3 plus 2i, x equals 3 minus 2i. Because complex always come in conjugate pairs, we have x equals 4, and now we're going to build our factors. So let's start with the real solution here. If I subtract 4, x minus 4 equals 0, that's fine. And here's what that says. I'm going to start building our function right now. What that says is that if I have x minus 4 equal to 0, then x minus 4 is going to be a factor of some polynomial with an x-intercept of 4. It's going to be a factor for us. And if this looks familiar, it should, because we've done this before, but we had all real solutions. Now, a couple things I want to say. This is where your multiplicity comes in. So if x minus 4 is a factor, and it says, well, check out what your multiplicity is. X equals 4 was a solution, sure, it was a 0, sure, but it had a multiplicity too. What that really means is that x kind of equaled 4 twice. Well, what's that mean? That means that really, we're not showing it, but you would have this other factor, x minus 4, and you'd have x minus 4 and x minus 4. You would have a repetition of that solution. Well, we all know that if I combine that, I would get x minus 4 squared. And that's really how we use our multiplicity. You don't have to show this. This is redundant, because multiplicity wraps up this idea and says, yeah, you're repeating that factor twice. So we would have x minus 4 2 times, and that multiplicity stands for the power of the factor from where you get your solutions. That's what that is. And so when we read, they go, okay, here's x equals 4. Cool. Here's x minus 4 equals 0. Okay, by the zero product property, sort of in reverse, I know that's a factor of some polynomial where 4 is an x-intercept, and it's told me that's a multiplicity 2. That stands for 2 x-intercepts. That stands for 2 of our degree. So we need to have this kind of add up to 4 as far as our degree. The last thing, we've seen this already, I'm not giving you a point here. I wouldn't say there's no point, but there's a point to this, which means that you can't say that this is the only polynomial that's creatable with these solutions. And so we put an a out there. Even if I had given you a point, you'd still put the a, because we'd use that point to solve for a later, and I'll talk about that when we get there. So we go, okay, real solution, we've done this before, x equals 4, cool, we have this factor, x minus 4, multiplicity 2 says you've got a power 2 on it, and this could stand for a lot of different functions that have these x-intercepts, but we don't have a point. And so we can't really solve for a even right now. Now, the complex, this is where it gets, I'm going to get these more complex, it gets a little more complicated. So we're going to solve this for 0, just like we did right here. We're going to subtract 3, we're going to subtract 2i. I want you to do it that way. I don't really want to see x minus 3 plus 2i in parentheses. That is what you would have if you went straight to your factors. You'd say, all right, this is x minus 3 plus 2i. And you might have seen that. You might have been taught that before. But in order to distribute well, you actually have to redistribute the sign and then regroup x minus 3. It's a little more difficult to do than what I'm going to show you. So solve for 0, subtract 3, subtract 2i. So we get x minus 3 minus 2i equals 0. Now, this right here is a factor just like x minus 4 was a factor, but we're going to think of it a little different. Here's how I want you to think of it. I want you to think of it as x minus 3 is one factor, and so we're going to group that. Notice that when we group the first 2 terms, we're not affecting this sign. There's no redistribution of a sign or anything. We just want to think of this as x minus 3 minus 2i. Here's why. So you get there or you understand when we get there. We're sort of treating this like 2 terms because we know that distribution with 2 terms is a lot easier than distribution with 3 terms and 3 terms. So 2 and 2 is easier than 3 and 3. Also, our first 2 terms are going to be the same here. Why? Because with complex conjugate pairs, your first number is always the same, 3 and 3. The second one has the change of sign. So if we group the first two terms, we're basically going to get x minus 3 times x minus 3. And we know how to do x minus 3 squared. It's not that hard, but that's why we're thinking of grouping them. And that doesn't really show up very well if you try to distribute 3 terms on 3 terms, or if you go straight to your factors, which is why I'm teaching you this. Let's do the next one. We're still going to solve this for 0. So x minus 3 plus 2i. So we're setting that equal to 0. And again, likewise, we're going to group the first two terms. This is the factor that I want you to have in your polynomial. So, long story made short, if you have a degree 4, you're going to have 4 factors. Now, some of those might have a different multiplicity, which counts. This counts as 2 factors. So we have 1, 2, 3, 4. And since these are all set equal to 0, we can use that zero product property to say, hey, this would be some polynomial with these 3 factors set equal to 0 based on the fact that you have those 3 solutions. I can't say x-intercepts anymore. I can say zeros, but I can't say x-intercepts anymore. And the reason why is because that is an x-intercept, but these ones are not. That's an x-intercept with a bounce. If you remember, at x equals 4, it would bounce either this way or that way because we don't have an a. There's no really way to know, but that is an x-intercept. These are not x-intercepts. They're zeros. They're complex solutions. So we're going to say, hey, there's one factor, multiplicity 2, and we have 2 more factors. So we're going to write with some brackets, here's the first one, x minus 3 minus 2i and x minus 3 plus 2i. These are all the factors that we have based on our degree. So we have x minus 4, here's 1, 2, here's 3, here's 4 factors. It's a degree 4 and that always matches up. There's 4 solutions. One's just repeated. So here's 4 and we would have repeated that twice. I showed that already. Here's another one, here's number 4. Now we got to distribute. I'm going to give you the minimum distribution and sort of the maximum distribution of what you would do here. The minimum distribution is you have to at least distribute your complex factors. You got to get it into linears and irreducible quadratics. Well, we don't have that. We have basically a repeated linear and we have 2 sort of linear factors with complex numbers in them. Because we have a degree 1, we have degree 1. So we lose some of that terminology, but that's basically what we have. This is not acceptable to leave for like anybody, even me who's sort of loose on distribute the whole thing because I want to punish you. It is punishing. If you have to distribute like with a degree 7 or something, that can get pretty nuts. So at least distribute the complex factors, and that's really what I'm giving you these for, is because in the next few videos, you have to know how to do that in order to find all the solutions if I'm giving you a complex solution. So you have to know how to do that. So let's practice it. This is the whole reason why I want you to write this, solve it for 0, and treat this as your factor with the first 2 terms grouped. The reason why is because you're going to start here when you distribute, not here. Start with your complex. That's the least you need to do, right? So start with the least you need to do. And when you distribute it, we're going to treat this like 2 terms and 2 terms. So when we distribute, because we've grouped those first 2 terms in each factor, we're going to think of this as x minus 3 times x minus 3. But what is that really? Well, that's x minus 3 squared. Now, notice what else happens. Because we grouped this sort of intelligently, because we grouped it, instead of 3 terms and 3 terms, you have this sort of difference of squares idea. Do you see it? Like you have the same, you basically have conjugates. You have the same first 2 terms, x minus 3, we're treating that as a term, and then minus 2i and plus 2i. What's going to happen when you distribute? Well, I'm going to show it one time, but I'm never going to show it again. If you were to continue to distribute, you would get x minus 3 times positive 2i, and you would get x negative 2i or minus 2i times x minus 3. Even though they look weird, remember that those would be your middle terms, and they're going to cancel every single time. That's the second reason why I want you to write it this way, is because you create for yourself And this will always happen with conjugate pairs. You get sort of this difference of squares or conjugate factors, where your first two terms are the same. In both cases, you have a different sign and your last term is the same. And so when you distribute, your middle terms will always cancel out, and that's nice. So setting up this way is really convenient. We have x minus 3 times x minus 3. Oh, okay, x minus 3 squared. Plus and minus the same thing. We really never show that. And then lastly, we just need to distribute the last two and be careful with it. This will be minus 2 times 2 is 4. I times I is I squared. You need to know how to multiply this complex. So I times I would be in the intermediate algebra class, but I times I would give us I squared. What we need to understand about I is that the square root of -1 gives us I, and because of that, I squared is always -1. So whenever you see I squared, you go, oh, that's -1. Essentially, what's that do? So if I squared is -1, it doesn't really change the value of 4. Multiplying 4 times 1 is going to give us 4. But because I squared is -1, it's always going to change this sign to a plus. So here's some truths about complex numbers. Think about these, maybe write these down. Number 1, complex solutions always come in pairs for polynomials. Always, because they're always from irreducible quadratics, and they're always, by the quadratic formula, going to give you plus and minus the same thing. So same thing, plus and minus the same thing. Well, that always creates for us these sort of conjugate factors, which means two things for us. Number 1, when you maybe 3 things. When you distribute, your middle terms are always going to cancel. That's great. It also means you're always going to get a minus here, no matter what. No matter what, because you'd have a conjugate idea. Minus and plus, when you multiply, that's going to give you a minus every time. Different signs give you a minus when you multiply. You're also always going to get an I squared. So if this is always a minus, and that's always going to be I squared, the I squared is -1. It's going to essentially just change that sign. So you should always end up with some sort of a linear factor that you have to square. So you're going to do x minus 3 times x minus 3. That's x squared minus 6x plus 9. But you're always going to end up with plus some constant. If I squared is really -1, then this would really be -4, and subtracting -4 would give you plus 4. Those are some facts about those complex solutions. I always give you this idea, middle terms are going to cancel. You get minus something with an I squared. That I squared is -1. It'll change that sign to a plus every time. Check that. Check for that. So this is really what we want to distribute now. So off to the side, maybe we do x minus 3 times x minus 3. You can do this in your head. What you can't do is you can't go, oh yeah, x squared plus 9 or x squared minus 9. That doesn't work. What we get is this x squared minus 6x plus 9, and don't forget that we have this plus 4. That plus 4 is this tacked on thing because this is still in this sort of factor. Like, this is what we're creating. We're creating an irreducible quadratic factor. And that's it. So we end up getting x squared minus 6x plus 13. And that actually is an irreducible quadratic. If you try to factor that, you can't do it. Quadratic formula is going to give you, oh, wait a minute, complex? So basically, we're going opposite of that. So the last thing that we need to do as far as the minimum work here would be to bring down our linear factors that came from our reals, even if they're repeated. So like x minus 4 multiplicity 2, bring down our a because we really don't know what that is. And then that's good enough for me. That's fine. Now, some of your teachers or instructors, or maybe you'll want to distribute this a little bit more. So what you would do here, and this is the only time I'm going to show you this, what you would do here is you would distribute this x minus 4 times x minus 4. Very similar to what we did over here. You'd get x squared minus 8x plus 16. And then you'd spend the time to distribute 3 terms onto 3 terms. Notice if you don't use my technique, that's exactly what you'd have to do up here if you didn't group those, and That's a pain in the rear because you have lots of stuff floating around, lots of sign errors happen, lots of little mistakes happen. So hopefully you agree with the distribution of complex numbers when I'm doing it. It's the easiest way I've ever come up with to do that. Then you distribute this. What I'm going to do is just give you the final answer, what you would get for your polynomial. So some math magic happens and you get that after you distribute. So we take this term times all of these, and then this term times all of those, and then this term times all of those, and combine like terms, and that's what you would end up with. So what do you do with the A? Number one, don't distribute the A. Not right now, at least. What you would do is if you're not given another point, you're done. This is a polynomial that would have this would be a degree 4. Look, degree 4. This would be a degree 4 polynomial that would have these zeros, and that's the only real zero with a multiplicity 2. This is it. If you had to refactor it, you have to go through all of this work again. So don't do that. So if you don't have a point, you're done here. If you get a point, so if someone gives you a point, like, hey, I'm going to make this up, this is not a point for us, you would say if we had one point that's not on the x-axis, so you can't use something we already have. Let's say it's like 1, -3. If it was 1, -3, what you do here, you'd plug in 1 for your x's, you'd plug in -3 for your y or your f of x. You'd simplify this, divide, and a would equal whatever you have. So x goes for x, y goes for y or f of x, and then you solve for a. Once you have that number, then you can rewrite it with a, whatever the a happens to be. Then you could distribute that a through it. Even if it's a fraction, it can be very nasty. But that's something that you could do. I hope that makes sense. I'm going to leave it here. This is basically for a polynomial, leave it here. If you had a point, you'd have to go through and do that. You could leave it here and do the same thing, like put in 1 here, here, and here. Simplify, put -3 here and divide. You could still figure out your a from that part. So that's fine as well. This would be the very minimum of what you'd want to do. This is factored into linears and irreducible quadratics with an a in front. You could, if you had a point, you could plug it in here even and still solve for a by the technique I just showed you. If you have to distribute, this is it. So you want to go all the way down to that. Okay, let's move on to the next one. We're going to go a bit quicker on these because I've already sort of given you the whole idea. So we have 2 more examples. This one and then a degree 5 I want to work through with a different multiplicity. So we see a degree 4, and what that means is a few things. Number one, we will need to have 4 factors, some of which will have some complex numbers, and we need 4 solutions. So they've only given us 2. Well, what that means is that we're going to have to find the other 2 and build some factors from that. So when we look at them and go, hey, they're both complex. We know that complex numbers or complex solutions come in conjugate pairs. So let's work on that. If they give you 1 plus 2i, then 1 minus 2i also has to be a solution by the quadratic formula. If they give you positive I, then negative I also has to be a solution. Remember that positive I really is 0 plus I. There's no real part here, there's just an imaginary part. The conjugate would be 0 minus I, or just negative I, because you wouldn't have to write 0 for the real part. Now, as I mentioned before, we really need to write out those solutions as x equals that so that we can get an appropriate factor. Much like we've done over here, it just makes it a lot easier to see. Otherwise, you have to sort of manipulate signs. We all know sign errors are real kind of a bugger for us. So we want to do it this way to make sure our factors are just perfect. So we're going to write out that x has to equal I and negative I. X has to equal 1 plus 2i and minus 2i. So that represents our 4 zeros. We have I, negative I, 1 plus 2i, and 1 minus 2i. So I'm just checking my work. I'm going to make sure that I have 1, 2, 3, 4. It's a degree 4. There's no multiplicity, at least not with these complex solutions, so we're good. Then what we're going to do is we're going to set all of these equal to 0, and that's going to give us our factors. So subtract I, add I, subtract 1 and subtract 2i, so x minus 1 minus 2i equals 0. Subtract 1, but add 2i, and x minus 1 plus 2i equals 0. Then what we're going to do is, these look pretty good. If you notice, because there's no real part, this is going to be a little easier to distribute. There's really only 2 terms and 2 terms. You don't have to group anything. We grouped over here because we had a real part that was the same, so 3 and 3. We grouped it with x minus 3 so that we could get x minus 3 squared when we distribute. That was really nice. Because we don't have that real part, that's not really an issue for us. So we're going to have 2 factors, x minus I and x plus I, because both those factors equal 0. By the zero product property, we know those are 2 factors of a polynomial that has those things as solutions. I can't say x-intercepts because those aren't x-intercepts, but they are solutions. Now, for our other complex solutions, we're going to create some factors by just grouping the x with the real part. And like we did before, what that does for us, because the real part's always the same in the complex conjugate pair, that is going to create an x minus 1 squared when we distribute. We treat this like one term in distribution. So we have 2 terms, 2 terms. We're going to treat this like 2 terms and 2 terms. So let's go ahead, let's write out our polynomial. We are going to give us an a because, again, it's not giving us a specific polynomial. It's saying, find me a polynomial that has these solutions. You're all right, well, all I have to work with is factors. I really don't have a point to work with. But because I have all these factors set equal to 0, I know that I can create this polynomial that's going to have those solutions by just using those factors. If it's a degree 4, you should have 4 factors. That includes some multiplicity, but you should have 4 factors. So this was, each of these factors set equal 0. I could have created a polynomial equal to 0 by the zero product property, or just gone straight to my function and said this is a function that would have these as solutions, because by the zero product property I get all those factors equal to 0. There's 1, 2, 3, 4 of them for a degree 4. It's looking really good. All we have to do now is go through the same process and distribute our linears that have complex numbers in them, these conjugate pairs. So we're going to distribute that. We're going to leave it there. If you need to go further, you'd have to keep distributing. So I'm going to start with this over here. I always like to attack the hardest looking ones first. So I'm going to distribute and think of these as 2 terms times 2 terms. We notice it basically is a conjugate right here. If you think of this as one term, this is same thing with a different sign between them. That creates like this difference of squares idea for us, where we're going to get first term times first term, x minus 1 squared. If you went ahead and distributed it, you'd get plus and minus, the same exact thing. They're going to simplify away. They're going to cancel out. I don't even write them. What we do have to realize is that because these act like conjugates, you're always going to get a minus some imaginary number squared. So you're going to get negative 2i times positive 2i. Well, that's minus. 2 times 2 is 4. But I times I is not just I. You're going to get I squared. And we walked through this before, where what that I squared is, that I squared is negative 1. So 4 times negative 1 is negative 4. Subtracting negative 4 is really just adding 4. It's exactly like this, even down to the number. So that's plus 4. If we do that x minus 1, you can do it in your head. Just don't give me x squared plus 1 or x squared minus 1. Remember that this is x minus 1 times x minus 1. So that's going to be x squared minus 2x plus 1. And then we also have the plus 4. Let's not forget about that. That needs to be added to that constant. So we've distributed this. It was this piece, but then remember we have the plus 4. And that right there is an irreducible quadratic over the real number system. That's an irreducible quadratic for our factored polynomial. All of this would be in some sort of factor. And then we're going to do the same thing here. It's just going to be a little bit easier because we don't have this distribution of these two terms squared. So when we distribute this, you can really see this as a conjugate. If we distribute, we're going to get x squared, but we get plus ix minus ix. Well, when you add those together, they cancel out, so we don't even write them. That is a conjugate. The middle terms are gone. And then minus I squared. Notice negative I times positive I is negative, so we write minus I squared. But what is I squared? Well, I squared is negative 1. So this would be x squared minus negative 1. That's what I is. It would look just like this. Sounds so weird. That's what I is. So you're really subtracting negative 1. The same exact idea over here. This is not a really awkward thing. This is saying what you're really doing is subtracting 4 times negative 1. That's what we're doing here. We're subtracting negative 4. That's what we're doing here. So we're subtracting negative 1. And that creates this other factor. It's also an irreducible quadratic. It has to be. That's what these irreducible quadratics create, is factors over the complex. So, factors with imaginary numbers in them over the complex. So these linear factors with complex. So if we have two linear factors of the conjugate pairs and we start distributing them, it's going to give you something that's an irreducible quadratic over the reals. If we put our a down here and say, hey, this is a function that would have those 4 solutions. This is actually a degree 4. Think about it. X squared and x squared would be a degree 4 polynomial, just like we said. With these as zeros, they're not x-intercepts, but they are zeros. These are 2 irreducible quadratics. We're done. If you have to distribute after this, you'd start and just take your 2 terms times your 3 terms, combine your like terms after that, and leave your a in the front, just like we did here. If you wanted to solve for a, you could certainly do it here, but you need a point to do that. So if we had an x and a y, you plug in your x's here, your y here, simplify the side, and then divide to solve for a. Then put your a right back. Do the same thing if you distribute. You just put your a in front and then distribute the rest of the way. So I hope that makes sense. I'm going to come back with one more example. It's quite similar, but I just want to make sure that we see it one more time. All right, let's give it a shot. Actually, what I would strongly recommend is that you pause the video and you try this on your own. So try setting up these factors. Try getting the one real factor that we have, creating or one real solution we have, creating the factor for it, using the multiplicity, creating it as part of our polynomial function. Then check out your conjugate pair, take and set those equal to x, and then make it some factor equal to 0, use that, distribute those complex conjugate factors that you have, and then see as far as you can make it with your distribution. Remember, we have to at least distribute so that we don't have any more complex numbers in there. We need an irreducible quadratic from those. So let's go ahead and get started. If we have a degree 5, that means we're going to have 5 factors, and multiplicity might count for a couple or 3 of those factors. But we definitely need to have 5 added up together, if you will. We also notice that we have one complex solution. One complex solution always comes with a pair. So right off the bat, we're going to say this also has a solution of 1 minus 2 minus I. Now let's go ahead and set these equal to 0. So our solutions are x equals 1, x equals 1 plus I, and x equals 1 minus I. That's really it. That's all the unique solutions that we have. Now, why we don't set this equal to 1 3 times is it's just redundant. Multiplicity says, yes, you do have 3 factors, each of which would give you the solution of x equals 1, but we know a little bit more than that, that multiplicity really just stands for the exponent of our factor, because that's the same thing. X minus 1, another x minus 1, another x minus 1 would be x minus 1 to the 3rd power, and that's exactly what we're going to get here. So we set our x's equal to our unique solutions that are given to us. And then we solve them. So x minus 1 equals 0, that looks pretty good. We're going to solve both of these. X minus 1 minus I equals 0, and x minus 1 plus I equals 0. But we're going to be smart about it. Because these are going to create some complex factors for us, we're going to group the x and the real part. Because that real part doesn't change for your complex conjugate. It can't change. So that when we distribute, when this and this are factors, x minus 1 gets multiplied by x minus 1, creates x minus 1 squared. It's a lot easier to work with. That way you're only thinking of 2 terms times 2 terms, and you can use a lot of the advantages of the conjugate pairing that we saw. Otherwise, you're doing 3 times 3. It's way overcomplicated. So now that we have these 3 factors, we're going to start building our function. We know that this is just one of many functions, like a family of curves, that could have these as solutions. So we're going to say what each of the factors is. We have an x minus 1. We have x minus 1 in parentheses minus I. And likewise plus I. You can see it, right? If we set this equal to 0, we'd get this and this and this equal to 0 by the zero property. We're just going backwards. The only thing I've left out, hopefully you notice it, is that x minus 1, that came from a 0 that had a multiplicity of 3. So what that says is that if this x equals 1 has a multiplicity of 3, really there are 3 factors that each of which would give you this x equals 1. It's still a crossing of the x-axis, but we need to represent this as a power 3. We've got to make sure our degree matches. So this factor counts for 1, 2, 3 factors. It's just written more concisely. That's what exponents do. 4, 5 factors looks really good. Here's 1 solution, 2 solution, and because it has a multiplicity of 3, that really counts for 3 solutions, because you could have written out x equals 1, x equals 1, x equals 1. It'd be redundant, but you could have done it. Now what we're going to do is distribute at least the factors that have complex numbers in them. Because we wrote these appropriately and grouped our x with our real part, it makes it really nice because these are legit complexes, conjugates right now. So we think of this as one term, and we get x minus 1 squared. Again, this idea is used a lot in the next video, or whenever you have to multiply some complex factors together, and we're going to do that and then do long division in the next few videos. So x minus 1 squared, great. We get plus and minus the same exact thing, and what we've come to expect, we're going to get minus some sort of imaginary number squared. Now what that imaginary number squared does is gives you -1. Okay, well if we have a constant associated with that, like 4 times I squared, that'd be -4. Here, this is literally just -1. So we are going to get this x minus 1 squared minus -1, or x minus 1 squared plus 1. That's really what we have. When we distribute this and combine it with plus 1, we get x squared plus minus 2x plus 1. That's going to give us x squared minus 2x plus 2. That's going to be our irreducible quadratic factor at the end of our problem. We really don't have to distribute that unless you absolutely have to. And they say you must distribute. Then what you really have to do is do x minus 1 times x minus 1 times x minus 1, which gets really tedious. Distribute this one, get some sort of a quadratic, not irreducible, some sort of quadratic, and then distribute another x minus 1 across it and combine some like terms. Then you'd have to take a 4-term polynomial times a 3-term polynomial, you get 12 terms. Then you'd have to combine them. And you're going to have some like terms, but that becomes quite tedious. For me, it's not necessary. If you have to, then you have to. Personally, I like this because I've already taught you how to find a leading term by doing that sort of fake distribution thing. I've already taught you what to do with our linear factors with multiplicity. That's going to have an x-intercept of 1, multiplicity of 3. It's a cross. This is an irreducible quadratic. It doesn't give you any additional x-intercepts there. So this is a factor that would have the solutions as they told us it would. Again, if you had to distribute, you do this, then distribute this, don't distribute the a. If you have a point, this is when you plug in. Plug in your x, plug in your y over here, and solve for a, then put it back. Then you distribute that a through after you distribute all of this stuff. That's about as far as I want to go on that. I hope it makes sense. especially the how we write these complex factors and distribute. That's the biggest thing I wanted to show you, and to make sure that our degree actually matches. For instance, if we did this, we know our leading term is going to be x to the third times x squared, fake distribution. We talked about that already. That's going to be an ax to the fifth. That's the leading term of this polynomial. It matches the degree that they've told us, and depending on the a, we'd have an end behavior that is odd or negative odd. So I hope you're with me. I hope you're enjoying the videos. Next time what we're going to do is we're going to start talking about how to find all the solutions of polynomial functions, including some complex. So sort of some similar ideas here. We're just going to really flesh it on out and make sure that we really understand how complex works with polynomials. So I'll see you for that.